Welcome back to another example, grade 11th. In this example, you're going to see that we're going to make use of what we know about vectors in 2D. We're going to make use of the tail-to-head method as well as trigonometry. So this example says two small identical metal spheres, X and Y, each with a mass of 10 grams, hang on two equally long wires which are attached to the same fixed point. We have their masses, both of them have the same mass. It's 10 grams, but we convert to the correct SI unit by dividing by 1000 or multiplying by 10 to the negative 3. They say when the spheres received equal charges, so in other words, when Qx, the charge on X, is equal to Qy, right? And remember, from the previous example, we can say that this is equal to Q. What happens is that they repel each other, and they then move a distance 40 millimeters apart. So we know that R is equal to 40 millimeters, which means the same as 40 times 10 to the negative 3 meters, or you can say 40 divided by 1000. The angle that the Y is made with the vertical is 45 degrees, and you can see that in the sketch. Now they say, answer each of the following questions applying to the spheres in a state of rest as illustrated in the diagram. Very important, whenever they mention a state of rest, do not ignore it. We're using Newton's laws here, which says if the object is in a state of rest, then the net force is 0. And this is important information because firstly, it means when you sum up the forces, we're going to end up with 0. But it also means that if we use a tail-to-head diagram when drawing the vectors, we're going to end up with a closed vector diagram. And we're going to be making use of this in this example. Now, question number 1, we're going to skip because it asks about force diagrams. And we're going to go straight on to question number 2, which says, draw a free body diagram that shows all the forces acting on Y. This over here is object Y. So we're going to represent object Y using a dot. We know that there's a wire pulling up on object Y. So we call that a tension force. Object Y has a mass, so therefore there's a gravitational force that the Earth is exerting on object Y. They said to us that the charges are exactly the same and that the two spheres are going to repel each other. That means that X is going to push Y away. And therefore, on our diagram, on this free body diagram, we're also going to include an electrostatic force, Fe, towards the right. These are all of the forces that are acting on sphere Y, and this is the answer to question number 2. So now we can go on to question number 3. It says, calculate the magnitude and direction of the electrostatic force that X exerts on Y. Now please, grade 11s, this is really important information and I want you to hang on to it until matric. The formula Fe equals K, Q1, I'm going to use Qx, Qy in this case, divided by R squared. Whenever you use this formula, when you plug in the charges, you only plug in the magnitude of the charges. This is because this formula only gives you the magnitude of the electrostatic force. If you are interested in direction, then you are going to look at what type of charges you're dealing with. If we have negative and negative, they're going to repel. Positive and positive, they're going to repel. And positive and negative is going to attract. That is how you're going to determine the direction. So let's start off by finding out the magnitude. We have the equation. Let's see if we have enough information to calculate this electrostatic force. We always know K, and we've been given the distance between the centers of the two spheres. But we don't know what the charges are. All that we know is that the charges are the same. So this formula is not going to help us. But remember, grade 11s, I said to you, the objects are at rest, which implies the sum of the forces is 0, and that if we draw a tail-to-head vector diagram, if we use the tail-to-head method to add our vectors together, we're going to end up with a closed vector diagram. So let's take all of the vectors, the forces that we drew in question number 2, and let's add them together using the tail-to-head method and see what we obtain. So let's start off with the gravitational force. You're welcome to start off with any force. I'm going to start off with Fg because I know that Fg is straight down. So here is the gravitational force, and we're going to label this force Fg. To the head of Fg, we're now going to attach Fe. You're welcome to attach the tension force if you'd like, right? But I'm going to use Fe first, and there is Fe. Then to the head of Fe, we're now going to attach the tension. And as you can see, we end up with a closed vector diagram because the net force acting on y is 0. Since Fg is straight down and Fe is parallel to the ground, we know that we have a 90-degree angle over there. So we have a right angle triangle, and the trig ratios will therefore work. There's another angle that we have. It is the 45 degrees that was given to us, and that is the angle between Fg and the tension force over there. So we look for where Fg is and where the tension force is. It's here and there. And in between them, we're going to place a 45-degree angle. This is a diagram that we can work with in order to find the missing Fe. We're unable to calculate the tension, but we can definitely calculate Fg because Fg is the force that the Earth is exerting on the object and is equal to the object's mass multiplied by 9,8. So the object mass is 10 times 10 to the negative 3. G is 9,8. And when we plug this into our calculators, we end up with 0,098 newtons. This over here is the gravitational force. We still need to calculate the electrostatic force. So we know this side of our triangle is 0,098 in its magnitude. We have this angle, and relative to that angle, the tension is the hypotenuse, Fg is the adjacent side, and Fe is opposite. So we have the adjacent side and we have, or looking for, the opposite side. So that means we can use tan in order to calculate Fe. We say tan theta is equal to Fe divided by Fg, the opposite side divided by the adjacent side. Therefore, tan 45, which is the angle, is equal to Fe divided by 0,098. We multiply up by the 0,098 and we find out that the electrostatic force is equal to 0,098 newtons. We're not done yet because this is only the magnitude of the electrostatic force. The question asked for magnitude and direction. We said both of these objects have exactly the same charge. So therefore they're going to repel each other. And if we go back up to the sketch, we know that y is going to be pushed away by x. X is pushing y away. So therefore, we know the force, the electrostatic force on y is going to be towards the right. And this is the answer to question number 3. We have the magnitude and we have the direction. Always ensure that you answer these questions fully as far as possible. So always go back and check what the question said. It's very easy to miss or to leave out direction, for example. Question number 4 now says calculate the magnitude of the charge on each sphere. We know that each sphere has exactly the same charge, which we are substituting into the formula as Q. So now we can make use of Coulomb's law. We say Fe is equal to K, Q, in this case Qx, multiplied by Qy, all of this divided by the distance between them squared. K is the proportionality constant. It's 9 times 10 to the power of 9. Qx we're going to sub in as Q, and Qy we're going to sub in as Q. Now Q times Q is just going to equal to Q squared. So instead of writing Q times Q, I'm just going to plug in Q squared to spare us a bit of time. We're going to divide this by the distance between them squared. The distance between them is this 40 times 10 to the negative 3 meters. So we plug in 40 times 10 to the negative 3, and we do not forget to square this. It's very easy to forget that. We put in the 0,098, which we calculated in the previous problem. And then we can manipulate this formula in order to solve. We're going to start off by multiplying up. So we multiply up and we get 0,098 multiplied by 40 times 10 to the negative 3 squared. We need to divide by 9 times 10 to the power of 9 to get rid of it, because we want Q on its own. Now that we've gotten rid of 9 times 10 to the power of 9, we need to get rid of the square on the Q, because we're trying to solve for Q. So now we're going to take the square root of all of this, and that is going to give us Q. Now grade 11s, if you struggle to solve everything in one step, that's not a problem. You're welcome to solve, or yes, find the answer using many steps. That's 100% fine. You don't need to do everything in one go. So in the end, the value we obtain for the charge is that Q is equal to 1,32 times 10 to the negative 7 Coulomb. And that is the final answer to this question, question number 4. Let's just make 100% sure. Yes, that is the answer. So we have completed this example.